Hello. So this question is from GATE 2023, and this is a question from electromagnetic theory or EMT, and this is a numerical answer type question. So the question states that two independent electrostatic configurations are shown in the figure. Configuration 1 consists of an isolated point charge Q equals 1 coulomb, and configuration 2 consists of another identical charge surrounded by a thick conducting shell of inner radius R1 equals 1 meter and outer radius R2 equals 2 meter, with the charge being at the center of the cell. Now W1 is given as epsilon naught upon 2 integration E1 square dV, and W2 equals epsilon naught upon 2 integration E2 square dV, where E1 and E2 are the magnitudes of the electric fields for configurations 1 and 2 respectively. Epsilon naught is the permittivity of vacuum, and the volume integrations are carried out over the all space. If 8 pi by epsilon naught and then the value of absolute value of the difference between W1 and W2 equals 1 upon n, then what is the value of the integer n? So this is the figure. So this is figure 1 and this is figure 2. So figure 1 is a case for a point charge, whereas figure 2 is a case with a point charge inside a conducting cell. So let me just draw some parts, clarify this figure 2 first. So this is a charge Q inside a conducting space. So let me say this as region A, this conducting space as region E, and outside this as region C. So due to conduction uh, of charge Q, this part would be negative, then there will also be positive charge in this part, then negative here, and I will get at the end, at the outer surface, positive charge plus Q. Okay, so let me just erase this inside due to charge conduction. So now let me proceed. So they want us to found the quantity W, which is, as we already know, this is the electrostatic energy stored inside the system. Okay, so this thing is we already know. They haven't included this term in the question. So the quantities which are they given is Q in both the cases are 1 coulomb, R1 equals to 1 meter, and R2 equals to 2 meter. Okay, yeah, fine. So for case 1, so here we know that the W1 is given up by epsilon naught upon 2 integration E1 square d tau, right? Or dV. Okay, E1 square dV. Now for a point charge, the electric field is typically given as 1 upon 4 pi epsilon naught q by r square. Also the volume element dV is given as 4 pi r square dr in a spherical polar coordinate system. So we get W1 equals epsilon naught upon 2 integration 1 by 4 pi epsilon naught q by r square whole square into 4 pi r square dr. Now the question comes, what should be the range of this integration? So the integration is typically from 0 to infinity, but I am not taking 0. Instead of that, I am considering an infinitely small quantity, let's say epsilon, which is a totally different, not to be confused with epsilon naught or the permittivity. So epsilon is a infinitesimally infinitesimally small quantity. Okay, and I am taking epsilon because I just want to avoid the situation 1 by 0. It is been considered to avoid the pole at r equals 0. Okay, so if equals to epsilon by 2, and then it is I can take it out, so it will be 1 by 16 pi square epsilon naught square, and also q square will also come out. The integration is from epsilon to infinite. It is 1 upon r power 4 into r square dr. So 4 pi will also come out. Okay, and so 4 to 4 pi epsilon naught epsilon. So it would be simplified as q square by 8 pi epsilon naught, and then it is from epsilon to infinity integration 1 upon r square dr. Okay? And this will give me q square by 8 pi epsilon naught minus 1 upon r epsilon to infinity, and this is q square by 8 pi epsilon naught 1 upon epsilon naught, okay, because 1 upon infinity is 0. So see, if there we have taken it as 0, then we have got a 1 upon 0. So this is not a very physical answer we are looking for. So to avoid that situation, I have considered the integration starting from epsilon, which is an infinitesimally small number, although the charge is located as r equals to 0. So epsilon is something r tends to 0. Okay. Now in the region 2, in case 2. Okay. So I have already modified the diagram here. So in case 2, you can see there are three regions: region A, region B, and region C. So charge is kept at region A at the center of the ring. Then the region 2 is a conducting region, conducting plane, let me say, and region C is outside the sphere, spherical part or outside the cell. Okay, so here I can say that W2 is equals to epsilon naught upon 2 integration, what do we say, E2 square dV. And this thing we can as, so E2 square can be say as EA square dV plus EB square dV plus EC square T, P. I think this is pretty clear. You can see A, B, and C regions. Okay, so let me proceed. Now, inside the conductor, electric field is 0. So EB equals 0. Thus, integration EB square BB equals 0. Okay, so we get W2 as epsilon naught upon 2 integration E square, which is 1 by 4 pi epsilon naught Q upon R square whole square into 4 pi R square dr, and the region here should be from epsilon to R1, where epsilon is the infinitely small quantity very near to the uh, center. R equals 0, and R1 is the radius of the uh, first region, or the boundary of the first region, and in the second region it is 0, and in the third region it is the integration from R2 to infinity, where R2 is the radius of the second concentric ring, and infinity because of we are intended to calculate the electrostatic energy due to this region over that space. And this is also as 1 by 4 pi epsilon naught q by r square whole square 4 pi r square d. Okay, this is the case. Now this will be epsilon naught by 2 into u square by 16 pi square epsilon naught square into 4 pi, and then integration epsilon to r1, and that is 1 upon r power 4 into r square dr, plus integration r2 to infinity 1 upon r power 4 into r square dr, and as we have calculated this earlier, this value is about q square by 8 pi epsilon naught, q square by 8 pi epsilon naught into, and this is integration epsilon to r1 1 upon r square dr, plus integration r2 to infinity 1 upon r square dr. And this is also a very straightforward calculation for q square by 8 pi epsilon naught. So this will give 1 minus 1 upon r from epsilon to r1 plus minus 1 upon r from r2 to infinity. And this will be q square by 8 pi epsilon naught, and this is minus 1 upon r1 plus 1 upon epsilon, then minus it will be 0, so plus 1 upon r2. Okay, so now we need to find the quantity, which is I think W1 minus W2. Let me confirm. Yeah, W1 minus W2. So W1 minus W2 is given by the outer quantity is same for both. So this one, then it is, what is that? 1 upon epsilon. Okay, 1 upon epsilon minus minus plus 1 by r1 minus 1 upon epsilon minus 1 by r2. So finally I will get q square by 8 pi epsilon naught into 1 minus 1 by r1 into 1 minus r2. So this is r1 r2 r2 minus r1. Now we put the values, put q equals 1 coulomb, r1 equals 1 meter, and r2 equals 2 meters. I am not considering the units here, because it will be taken care of. So this would be 1 by 8 pi epsilon naught by 1 into 2, this is 2, and 2 minus 1, this is 1. So this implies 8 pi epsilon naught W1 minus W2 equals 1 upon 2. Now, I think there is a typo in the question. If you just notice, let me just show. The question says about 8 pi by epsilon naught. So I think this should be transferred to 8 pi epsilon naught. And if we consider this thing, then we will see this is equals 1 upon n. Okay. So this half will be equals to 1 upon n, and this is given as n equals 2. I have checked the answer keys, official answer keys, and it is given the value is from 2 to 2. So I think there is a typo in this question, and this should be treated in this way. So the answer is n equals 2. Thank you.